And the second session, we are going to talk about how we are going to build agentic systems with Apache Kafka and Apache Flink. So my name is Olena. I work at Confluent. I actually came here from Germany, which is not as hot and as beautiful as Bengaluru. So very happy to be here. I'll hide this. Okay, matter. So today at this session, we are going to cover multiple aspects of building agentic systems, especially with data streaming applications and using Apache Kafka and Apache Flink. So we will go from anything about agents to the architectures which are commonly used to how we engineer the prompts and how we use RAG and other building blocks which we have when working with agents. And also, I will not have as beautiful and sophisticated demo as the one of about Peanut, but we will also be building something step by step to show how exactly you apply those building blocks for the agentic systems. But let's begin by talking what is agentic systems, or what is their types which we might have of those agentic systems, and what are architectures and kind of what are building blocks. And I hope that actually I will be able also to share some kind of recipes which you can use later when building your systems, because every system is different. It seems like a party, right? Like with the lights and with the sounds. So yeah, when talking about agentic systems and what it is, I have tons of opinion, like everyone on the internet. And if you actually will go and check what are those agents, you will find like plenty of different definitions. So instead of giving you my opinion, I decided I will just go to some reputable sources. And I was looking around of different definitions, and this one is from IBM. And IBM calls an AI agent as a system or program that is capable of autonomously performing tasks on behalf of a user or another system by designing its workflow and utilizing available tools. Out of this definition, what is important that we have a workflow, we have some kind of a tools, and the system can autonomously operate using them. So if we are thinking about agentic system, we can think of it as an autonomous, highly skilled specialist, which has a possibility or ability to organize workflows, to split, for example, tasks into subtasks, to coordinate actions, to collect necessary information, because often when we work with agents, and then right now you can also take all the agents which you encounter on the internet, you usually actually can go and collect additional resources from external data sources. Here we can be using semantic search or OLTP or OLAP databases, anything like that. Then, of course, we need a large language model which will be able to reason and use all that information, and also use the natural language processing while doing that. And finally, we have access to the tool set to do some particular operation. So this is an agent. All in all. However, when I was looking for more, because of what is an agent and what is not, there is a lot of debate on the internet. And I liked really this conversation or this article from Anthropic, which I wish I could hide. Oh, never mind. So there is so Anthropic developed a lot of systems using AI, and they also kind of were talking what is an agent, or what is agentic system, and what is an agent, and what is not. And what as they did, they actually said that agentic system can be anything from workflows to actual agents. And the workflows they defined where LLM and tools are orchestrated through predefined code paths. So this is where we have the more or less reliable workflow through which we execute a program. And they call it workflows, they call it still agentic system. Then there are agents where large language models dynamically direct their own processes and tool usage, maintaining control over how they accomplish tasks. This is more or less if you have looked into Operator from Anthropic or computers used from OpenAI, where you give a task to, for example, book a ticket, and then it goes and clicks everything on your laptop to perform the task. Or, for example, another example of this sophisticated agent is the one to solve GitHub issues. And actually, there is a board to compare different large language models, how actually they can go if they're given a task to solve end-to-end. They're given tools, for example, to modify a file and to run the tests. And they need to fix a number of GitHub issues. They are doing pretty well. So I don't remember right now. I think like 70% was when I was checking that board that the LLMs and especially the one from Anthropic was performing pretty well. So yeah, so we have workflows, we have agents. Both of them are considered to be agentic systems. Then when we are talking about building blocks of an agentic system, it is LLM with three particular possibilities. So we need to have a possibility to retrieve the data. We need possibility to access the tools. And finally, we should be able to work with memory. So this is, at least by Anthropic, the way how the building block of any agentic system. And there are plenty of also frameworks which we can use. And the framework, so I put at least this list definitely not all inclusive because the list of all the libraries we have is super huge. And generally, I wanted just to highlight a couple of those items and mention that if you are just starting working with agentic systems, and actually, can I ask you, raise your hand, who actually tried to build their agentic system either for a product or for personal use? We have some hands, totally cool, amazing. For those of you who are just thinking to start it, you might be tempted to use all the available libraries. Sometimes actually it would be an overkill because some of those libraries, they exist already for a while, but also we are moving very fast with APIs for the large language models and other models. And that's why maybe using those bloated libraries will be more of a disadvantage and you will be struggling with the library rather than LLM. But out of this list, what I wanted to highlight is a couple of things. First of all, just because I really liked the agents that tools which were introduced by OpenAI 2 weeks ago, I think, and it's they also have the agents SDK. Right now it's in Python, but they also plan to introduce at least JavaScript as well. And there you can actually have handoffs between agents and all the other tools. So it's a kind of really good example of how we can build a collection of agents which actually interact with each other. And second one is MCP. This is Model Context Protocol. A lot of people are talking about it. And we have the MCP also built by my colleagues at Confluent. And this is the way how you can use a large language model. And here we are talking about Kafka, Flink, Pinot here. So it's, for example, if you go there and you ask your large language model, could you tell me what are the current topics, or like what is the topics right now I have in my Kafka cluster? And then through this model context protocol and the server, we have the access to the APIs. So the model will get that knowledge how to call and list all the topics or do whatever other operations you provide through that server based on model context protocol. So this is evolving technologies also, like it was announced like announced 3 or 4 months ago, but people are starting to use it more and more. So we see a lot of those MCP servers. So that definitely worth checking because it has quite a promising future, at least from today outlook. So yes, but what I wanted to show, to go next into more or less architectures or like building blocks, how we are working with how we arrange the code when we are working with agentic systems. And the first one is kind of a simple. We decompose the task into a sequence of steps. So here we just have the large language model calls, and you're doing different operations step by step. You might actually run into some kind of a gate where you are validating if you are still on track, and if you're not on track and kind of maybe the task actually finished earlier, then you exit earlier. But it's kind of prompt chaining. Another one is to classify the input and then to direct the model to a specialized follow-up task. So this is where we can decide based on information maybe coming from the user. We will see the scenario a bit later, that we can call and redirect to a specific action done maybe by particular large language model. This actually can be also done, for example, if you decide that the task is simple, so you use a more like smaller model instead of using a bigger one. And if the task is complex, then you actually redirect it to a more complex, bigger model, which is more expensive, but you know that you need that power. Next one, we can do stuff in parallel and then aggregate and exit. Or we can use the orchestrator and kind of also delegate to large language models, then put all together. So all of this, and this is actually also, for example, this is an agent, how Anthropic sees it, so that we clarify the task initially, and then the large language model will be making those that work coming back to the user to clarify maybe some steps, or exiting when exit is needed, and finally performing the objective of what is provided by the human. And when we look at all of those architectures, they do smell of event-driven architecture. And this is also where I am exploring and I'm reading how people actually build those. More and more turn into as the idea that if we actually turn all of those blocks into events, we get our flexibility, or kind of like more control over the flow and a bit less roadblocks. So event-driven architecture and Apache Kafka and kind of data streaming systems are benefiting each other. So we have loose coupling, scalability, responsiveness, and all the beauties which we usually want to have from complex systems. And those agentic systems are complex systems. This is where we are calling, for example, like embedding model to get some vectors. When we are calling the large language model to some APIs for tools. So that's where, and since the topic also, I wanted to talk about Kafka and Flink, and Kafka and Flink are also building blocks of event-driven architecture. So that's also the way how it all brings together. And I think that actually agentic systems and all the tools which we use for event-driven architecture, they fit very nicely together, and we'll see more of the usage in the future. And I wanted to look through the a kind of a use case. This is quite imaginary use case, but let's see how we would design an agentic system specifically for pet owners. So let's say we have a one-step solution. Through whatever mechanism we let our customers to bring their questions, issues, or requests so that they can get information, or maybe they want to schedule some appointments or something else. So we have a mix of different steps which we might have, and how at least I suggest we can build this architecture, because it's all can be done, of course, differently, but how we can build it. For example, we have in some way getting a request from the customer. We might get the request, we still need to get additional information. So additional information can be, for example, additional information about the customer himself and his particular pet, whether it's a rabbit, a cat, or a dog, or whatever. So we get that from an OLCP database. then we might want to get additional resources. And this is quite a common use case where we use retrieval-augmented generation. I'll show it later, or semantic search, where we can actually connect maybe the documentation of that particular product or whatever other resources which we have. With that, we have that information of, like, it can be way more information which we collect before we are ready to send the request to large language model. But here we send and we try to triage the request from the customer, what exactly they want, what they just want information, or maybe they want to schedule an appointment or whatever they want to do. And finally, we exit once the job is done. So I will be showing some small snippets of the code. This is using the Confluent platform and Flink there. If you're using Flink elsewhere, there will be something different, but generally I wanted just to give an idea how it happens. So first we just add a value. So here I don't have a very fancy interface, but I wanted to share that technically we start with a Kafka topic. So for example, you have an interface and a customer sends a message. The message enters the Kafka topic. And then from there on, we can grab that information with a Flink and start building on top of it. So here I put that, and do you see it well, or is it? It's okay. Okay, cool. So here I just have a row where I have information on the customer ID, the conversation ID. So if you want to later to put all those together, we can, and also the customer message. And we have some kind of issue with the cat. So next, we want to collect information, as I mentioned, about the customer, about the rest. So when we are talking about agentic systems and we are talking how we are collecting the information or how we are working with the data, there are two, we can distinguish it into two groups. First one is embodied memory, which we have in the model itself. So this is the data on which the model was trained or the data on which the model was fine-tuned. And this is quite powerful. However, this is probably the minority of the use cases because not all the data you can fine-tune the model, and also not always you want to fine-tune the model because it's actually quite time-consuming and expensive. So it gets cheaper and cheaper, so maybe we will see more fine-tuning later. But again, not all the use cases you might want the data to be, model to be fine-tuned on. And the second one is Retrieval-Augmented Generation. This is where we just add the context into when we are calling the model, we are getting additional information from external source. So this can be done on the spot. And usually this is done when we want to get real-time details. For example, what is the weather outside right now? What is the, I don't know, latest stock price for some stocks? Or user-specific information like user details. And this is definitely, we don't want actually to give to the model to train the model on that. So we want to add it additionally only when we are calling the large language model. That also maybe like product documentation or any other specific knowledge on which the model was not trained. You know, when you're working with some when you're using, for example, ChatGPT to help you work with some APIs, sometimes it starts using outdated documentation because that's the documentation it was trained on. But actually, we want also to have maybe the fresher knowledge immediately. Of course, this is type of information, maybe it's possible if you could really easily fine-tune the model, such kind of a product documentation, maybe would be nice actually to fine-tune the model instead of giving it as a context. But again, often it's not really possible and it's more expensive. Any recent user-specific events, for example, on the shopping website, you are observing the actions of the user, what exactly they were looking at, what kind of products they were trying to buy, and so on, so that you can use it maybe for some recommendations. So this is the use cases which often retrieval-augmented generation is used. And type of data which we can have is plentiful. We are going to look at two of those fixed values from a database and using vectors and indexes, which I think kind of very common. I see more and more the knowledge graph being used, which is cool, but normally it's either fixed values or vectors. So yes, the flow of, so let's start with retrieval-augmented generation just to understand. This is something actually which we can pretty easily build with Apache Kafka and Apache Flink, but to get you an overview how if you are going to build it with either those technologies or anything else actually, how do you do it? So we get additional context from whatever source you have. The source can be anything technically, but the information which we retrieve, normally text information, actually, yeah, majority of large language models will accept text. So we get that information, and then when we are making requests to large language model, we just say, this is the problem you need to solve, and this is your additional context. So nothing more complex than that. So like retrieval augmented generation sounds very fancy and very complex, but technically it's just injecting extra context into the call to the model. Here I will show like two examples. First one is using the vector database. I used Pinecone. You can use Elasticsearch. You can use whatever database which supports the vectors. And I will use for customer specific info MongoDB. So in Pinecone, and this is how how overall like vector search works. Another kind of a building block which you can use in combination with Kafka Flink, but also outside of those worlds. So if you have some kind of a, let's say, documentation, you have your documentation for your product. It's very specific, so large language model doesn't know about it. What you do, you have you take your source files, you chunk it meaningfully, so not just randomly, because this is will not give you good results. But if you chunk it well, and then you transform those chunks into the vectors using one of the available embedding models, and then you store that in the vector store. So you will have your chunk of information, and next to it, you will have the vector. So we transform the text into numbers, and this is way easier for computers to compare. And then when you have the request from the customer related to the documentation which you have, you transform the request into the vector as well, using the same, and it's important, the same model. And then you take that single vector and you go and compare to all the vectors which you have stored in your vector store, and you find the closest vectors. Again, vectors like mathematical representation, so we can, it's usually a huge amount of dimensions. It's like 500, 700 dimensions or more. And you compare, and those dimensions representing different aspects of whatever data it is. So this is how vector search works. Here, for example, in the example I will be showing, I used Pinecone and I use OpenAI embedding model for embedding. So not to confuse with large language model, it's embedding model. So I have my Pinecone database, and I have some values here which I already prepared and injected, and they compare, they have also the vectors together. Then we go, and this is already the Flink world. This is actually how we use it at Confluent. So this might be a bit different from other versions of Flink, but this is how we define the model. And here we define the name, we define the information, how to access that embedding model, and what is input and output out of it. And here I can use that model to take the request from the customer and to transform that request into a vector, so that we can compare those vectors to whatever we have in the Pinecone database. So we can perform the similarity search. And next, if we look at the connection at the Pinecone, we do the same. We specify the Pinecone connection information, and we specify also what is the output information will be when I'm getting the response from the Pinecone. And Pinecone is a vector database, so it will return us when we are looking for similarities. Oh, yeah, so similarities, it will return as text plus embedding. So, and embedding is the same as a vector. So those two words are same, meaning same. And then if I will run that, I will get the information about let's see. So here I get the customer message. And also the information which I'm getting from the Pinecone database. So I'm getting the embedding and I'm getting the search results. So all those similarity results. So we get the information based on the request from the customer. We get what are the similar documents from the vector database so that we get a bit more context in this additional documentation, which we can use later to send to large language model for better requests. So that is specific information related to our product or whatever you have there. What happened actually when I'm running this with a Pinecone, I'm getting pretty long response together with the vector. And here I wanted to show another feature of Apache Flink. We create often user-defined functions to do some more sophisticated work. So here actually it's not really sophisticated. I guess it can be done also with SQL. But here what I wanted to do is to clean the response from Pinecone using a user-defined function. So I provide what kind of data I got, and then I provide a function how exactly to treat the data, and more or less I just extract the whole text and leave all the rest. But this is an example of I think it's very powerful also aspect. You can add those pieces of code which will process the data, even if maybe the main part happens like in SQL or table API, but this one is a fully working here Java. It can be also Python code. So, and here my goal was just like to drop all that vector information in the response from Pinecone and only get the values. So I should have shortened this initializing step. So yeah, so we have again the customer information initial what we got, and we are kind of increasing. And right now I have this relevant documentation about the health and medical advice, which we got from our documentation, which also can help us navigate large language model when trying to triage or direct the customer later. So that was the Pinecone. The second one is MongoDB, which I wanted to show. So MongoDB is a bit of a different beast. And with MongoDB, we can work actually in different ways. With MongoDB, we can actually make again either calls to MongoDB directly to retrieve that information, or because we have a connector, we can bring the data from MongoDB into Kafka. We must add the schema whenever we are working with Flink. Ideally, we use a schema because you want to have a very predictable result from your operations and not really mixing integers and strings and the rest. And here, if we create the connector which I did, I populated with the data with the MongoDB, and at the same time, I got it from the topic. And I saw that I do have all the information which I stored in the MongoDB. And that information there was just additional information about the customer. And customer, the email, for example, the age of the animal which they have. So everything which actually can help us later also to put it together to help the customer with whatever issue which they experience. And here, once we have that table actually in a Kafka, so we have that, and we can actually use just an inner join in Flink to bring together the information which we collected so far, and we have our customer ID. And on the other hand, we have another topic where we have also customer ID and customer information. So we bring those together and we end up with a table which has all information from both angles. You can do this particular like joining of the tables in many different ways, but I felt that actually if we can use a connector, that's pretty convenient. Also, we retrieve data only once. So next, the next one I wanted to show, because here we got some information, and I wanted to show you how the whole the use case with retrieval-augmented generation looks like. So we can create a large language model, and we just describe that it should expect some information from the customer and give the response. And then when we are making the request, here I'm using ML predict, and I put the information, all that relevant documentation, the customer information, the message of the customer, the pet gender, birthday, and so on. I put all together in the part of the prompt. So this is how we more or less inject that information which we retrieved from additional resources. And when we do that, we make request to large language model, and large language model takes all the information together and generates the response, and then it's generated some advice there. Cool. So that was when we looked, it was getting the information and also getting the recommendations. Let's look at actually how we can do the triage request. And for triaging, we are going to make another call to large language model, where we actually will tell the large language model, please please categorize the request into one of those 4 groups. So here I'm giving it predefined groups, either to get information or to schedule a vet or book grooming or raise an issue. And then in the call itself, we are defining also again all the information which we have, so that large language model can make that step. And if we run that, so here I had a bunch of records, and it was splitting me into, I actually get info and schedule wet mainly. So I got one of those values. But once I have that split into several groups, I can treat those differently, because I can create a new table which only has, for example, a scheduling request to schedule a vet. And then I can actually use some tools to work on the data. Again, with tools, it can be a request to the APIs, but it can be also, for example, how I kind of suggest in this particular demo, and this is a bit mocked, we store the events. We have a table. We have a table in Kafka, which expects, for example, to schedule event appointments, requests. And then we have another tool which will process the data. And when it's successfully processed, sends a message to another topic. In this way, we don't have the issues of maybe retrying or like dealing with some failed requests and so on. So it's kind of more stable than just calling API. And in this case, for example, so I have the appointment requests information, and then later I have the processed appointments, where I get information on the date and time of the upcoming vet visit. And finally, I can use also LLM to create a response and change those and create a response to get the final message to the customer. So that's what I wanted to share with you today. I also left 2 links. This is for the Confluent developer resources, which we have both in YouTube and as well as on the article. I really tried to publish the code samples, but I have a bit of a struggle with the GitHub system. And there will be soon, we are planning to write an article of this. So have a look on the developer Confluent. There are also other resources for working with machine learning and working with Apache Kafka and Apache Flink. Thank you so much for listening to me, and I'm all ears to questions. If you have any questions, I'm not sure if I'm running out of time. Should be okay. Okay, if you have any questions now or later as well.
In the RAG, when you query, there is a embeddings will be created, semantic search will be there. So we get some top and result, the additional results, right, in the RAG.
Yes.
Yeah. So the top 10, it's there is a chance that only the 7 will be relevant and the other 3 won't be relevant before sending to the LLM. Those informations, like additional information.
Could you repeat that? Sorry.
Okay, so when a customer did a query, right, that query creates an embedding and we do a semantic search in the RAG.
Yes.
So we get a top 10 results from the RAG. That
Yes. Yes.
also suppose 7 are relevant, 3 are not relevant for me, and we are sending that to the LLM. So won't it get hallucinating the output?
There is a hallucination is always an issue.
So how we are gonna counter that part?
We can actually do re-ranking on that as well. So there is re-ranking is where we got the results and we still try to filter out the ones which are good or not. It's called re-ranking. And this is the technique how to evaluate again whatever we got from the semantic search. But yes, it's true because we actually specify usually how many responses we want to get from the vector databases and just retrieves us that number of closest vectors, but neither of those can be helpful. However, I also think it will depend how good is large language model, because you retrieve kind of a bunch of resources, some is less relevant, but then a good large language model will skip those which are not relevant because it will just look for information which it needs. The more important stuff is that you retrieve really the necessary data. I think extra data is less of a problem. At least I see often then the large language model doesn't really use that extra data, but it says, sorry, I don't actually have necessary information in the context. So this is at least depends on the model, really depends on and the hallucination will depend heavily on the model rather than require the response from the vector search. Yeah. Any more questions? If not, I will be still here, so you can ask me after that. Yes. Thank you so much.